Okay, so let's start with 38 because that one was relatively challenging. So let's even start with the idea, look at what they've given you. Because if you start off wrong, everything is going to go wrong. So did they give you the radius or did they give you the diameter?
Yeah. That's why
They gave you the diameter, okay? So one of the things that you have to find is the volume, which is 4/3 pi r cubed, okay? So if that goes wrong, everything else is going to be wrong. So like if you use that diameter in there, you're wrong right from the get-go. So, couple little self-checks along the way. Your mass of the marble in kilograms, okay, should be something times 10 to the negative fifth and an okay GPA. Okay? So, when you find that mass in kilograms, it's an okay GPA times 10 to the negative fifth. But when you do the mole conversion, that has to be in grams. So you take the mass, okay, in grams, do a conversion from grams to moles. 1 mole contains 6.02 times 10 to the 23rd. Now, each atom of copper contains how many electrons? 29. So because the atomic number is 29. So at some point you need to use the fact that there are 29 electrons per atom. Okay? Then once you get this, then you can figure out, okay, hey, what's the total amount of charge? So then you got the 50 nanocoulombs. So what are you going to have to do with the 50 nanocoulombs? Convert that into coulombs. So what you're going to do is, on this one, then you got to figure out how many electrons there are. So at that point, at some point, you need to take the number of electrons that it took to generate the nanocoulombs divided by the total number of electrons on all of those carbon atoms. So you're going to get a very, very small value. Now, a couple of things about what this asks for. It says, what fraction? So this is not a percentage, okay? So do not get this number and then divide that by, and then multiply that by 100. It doesn't ask for what percentage of electrons. It just asks for what fractions. So let me give you some hints. So the total number of electrons that you're going to need to generate that charge should be something times 10 to the 11th. The total number of electrons on all of the carbon or all of the copper atoms are 10 to the 22nd. So at some point I need to see this, because so help me, if all I see is just, oh, here's my fraction and you have no work, or I don't see how you generated it, bad things are going to happen. At some point, I want to see what you divided to end up with that answer. Okay? So just keep that in mind. So that was a good one. On 40, because if 40 starts bad, everything's going to go bad. It says, what's the magnitude of the electric force on one proton due to the other proton? Okay? So extremely, extremely small distances, we use a measurement called a femtometer. Okay, that's a really, really, really small distance. Okay, and so that first answer on 40A should be around 60. Okay, because if that's wrong, it's going to be a train wreck from there on out. So the next thing that you want to find on B, on 40B, you got to go old school. F equaling big G M1 M2 over D squared. Okay, so you got to go old school gravitational force. So that answer should be 10 to the negative 30th, bless you, 10 to the negative 35th. And then when you divide that out, yeah, final answer on 40C should be something times 10 to the 36th. So you're going to go about 60, 10 to the negative 35th, 10 to the 36th. That's that sequence on that one. On 42, that charge is going to be something times 10 to the negative 7th. On 64, so 64 is, you really need to make sure that you can do 64 even in terms of the lab that you're going to do today. So if you look on 64, so you have two charged spheres, okay? Remember this when you do the lab today. This is a very simple type situation. So if you look at what's going to happen, if you isolate each one, you've got your gravitational force acting down, and then you have your tension going this way. But here's the story. Neglecting the buoyant force, which you can't in your lab today, but for this one you can neglect the buoyant force because of the fact that it's such a small fraction. So you've got the gravity pulling it down, and then so that means your normal force is just going to be balancing out that side. And then there's going to be an electric force that's going to push these two apart, okay? So that's the first diagram that you have to have, because if this is wrong, if you don't understand this part of it, everything is going to go wrong. So you've given a 2-gram ball, so you can find out what that gravitational pull is acting down. So then right away, you know what that side is on the upside of that. Cool. Now, you also know that on this one, you're trying to figure out what that, on 66, you're ultimately trying to find, no, 64. I was looking at the wrong one. On 64, you're trying to figure out the charge on this. So to do that, eventually you have to use FEC. So you got to figure out what the value of that force is. So on this, it's more of a function of geometry to a certain extent. So they gave you that angle is 20 degrees. Trust me, I'm glad you guys can do today. One of the biggest struggles you're going to find is finding that angle. Okay, and I'll tell you why. Because what you're going to do is you're going to charge two balloons and you're going to have them hanging by a thread, and they're going to be repelling each other. Well, as soon as you get near the balloons, what's going to happen?
They're gonna move towards you.
They're going to become attracted to you, and you're going to become part of the system. So I'm just telling you, the hardest part, one of the most difficult and challenging parts of this lab that you're going to do today is finding that angle, okay? Just saying. Just remember that when you do the lab. Like, oh yeah, Bert Kim told us about this. Yeah, I do. Okay. So, knowing that angle and knowing this side, there's a couple of ways you can do it. You really don't have to find the tension, because that isn't part of the story. If you wanted to, you could. But you need to figure out what the value of that electric force is. Then you can go from there. So the charge on each one on 64 should be between 7 and 800 nanocoulombs. Okay, so when you get done with everything going on, and the value of electric field, and then you can find the force and all this good stuff, then you can go from there. So there you go. On 66, that angle should be between 10 and 15 degrees. It's kind of a similar type idea. It's easier than 66 is much easier than 64. 64 is a tough one. On 68, so there's a couple of things about 68 that are important. So here's the bead, and on this one, you're told to free to slide on vertical rod, the base of the rod is okay, at equilibrium at what height above the fixed charge does the bead rest? So imagine this, here's this bead, and it's charged down here to, this is 15 nanocoulombs, and that's gonna be 10 nanocoulombs, okay? Now, what two forces are gonna be involved on 68? Charles, what's one of them?
Gravity.
Gravity's gonna try and keep the bead down. Okay? What else do you have?
Electric.
Now, which direction does the electrical force have to be acting? Jaden?
Opposite.
Yeah, because if your electric force was also pulling it down, it couldn't hover, right? It couldn't. So you know the force from your electric field is going to be pointing upward. Now, what's your net force going to equal? 0, right? Because it's not accelerating. So once you can figure out what that gravitational force is, then you can set that equal to your electrical field. So if all goes well on 68, in centimeters, it's going to be between 4 and 7. Charles, how are you? We're just rocking the wall.
Good.
Okay. All right.
Um,
Let me see. On the multiple choice questions, okay? On that first one, so you've got this action going on here, charge, 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 and then you've got your multiple choice answers, A, B, C, D, and E. So what I want to see in this space right here, and there's not a lot to do. What I tried to do when I typed this up was to guide you through the thought process on how to solve this problem, okay? Now, pay attention to what's positive and what's negative. So like on number 1, determine the electric field created by positive Q towards O. So this is a positive Q. So you got to start with this idea. Which direction is the electric field going to be directed from Q towards O? Is it going to go from O towards Q, or is it going to go from Q towards O? Q towards O. Because if you are a positive test charge, it's going to feel repulsive. So in this situation, that's being defined as a positive value. Even though it's in the second quadrant, it's pointing in the positive direction. So on number 1, that electric field is going to be KQ over R squared. And that's going to be a positive value. That's going to be in the X direction. So on number 4, I want 2 distinct answers. Jacob, listen to me. I want 2 distinct answers that I can easily see which is which. Okay? I want the sum of the X components and the sum of the Y components. Do not randomly write down 2 values and think, oh, Bergkamp will know what this means. No, Bergkamp won't know what this means. If they're positive, make sure you indicate that they're positive. If they're negative, make sure that they're negative. Let me give you a hint. One of them should be negative and one should be positive. Okay? So you're going to say, sum of the X components, boom, this. Sum of the Y components, boom, this. Do not just write down 2 numbers and go, Bergkamp will know what I mean, or Titan. No, we're not. Bergkamp will be frustrated and yell and scream. Okay, on the question about the uncharged spherical conducting shell, which is a big way of saying, hey, we have a metal sphere. So, it really doesn't make any difference what you put in there. It's kind of a cool thought process. It says, okay, we're gonna put a single electron inside of the sphere. So here's what you wanna think through. So you've got this negatively charged particle inside of here. Physically impossible to do, but it's a good thought experiment. So because of the fact that this is conducting, okay, look at what the chihuahuas are going to do on the inside layer of that shell. Look what the chihuahuas are going to do. Either the chihuahuas are going to move towards the center or they're going to move towards the outside, okay, because it's a conducting sphere. Figure out which one they're going to go. Then, once you figure that out, then figure out what's going to happen if you put a positive test charge on the outside of it. So based upon the movement of the chihuahuas in the sphere, that determines what the positive test charge is going to do on the outside. And here are your options. It's either going to get pulled in or it's going to get pushed away. Those are the only two things that can happen. Okay. On that last question on that backside with the 4 charges, okay, keep in mind you want to find the value of the electric field. I didn't take you through all of the math, but if you wanted to, you could do that and end up at that point. If the value of D flips you out, and you go, oh, man, I hate working with D, okay? Let the distance be 1 meter, okay? If that flips you out, okay? It's like, oh, let the distance be 1 meter. Do the math with 1 meter, okay? And then you can go from there, okay? So if the D's flip you out, don't let it, okay? Put in a distance of 1 meter. All right. Any questions on the assignment? Anything you want me to go over? Charles?
What were you looking for on question 19?
What do you mean?
What was the answer?
Is that the question about the plane?
Yeah.
Okay.
My dad was wondering what the answer was. Because he's a weirdo and he works on planes. And he's an electrical engineer.
That's clearly better than yours. Wow, your dad's knows though. Electrical
That's why he was.
Electrical engineer working on planes.
That's why he was
There's an
wondering.
issue there.
So you only need
The
to find the
electronics?
point.
Oh, that's kind of dope.
That's a beautiful plane.
That's kind of a good plane, honestly.
I mean, look at
That's a
it.
great plane.
Um,
that Delta? Or Southwest? What type of, what model is this?
And then you have a mass, which will further help you find the,
Wow, Prashant. Really?
It's a twin engine Joby.
Huh?
It's a really good plane.
yeah, that's on the table.
One of your better drawings.
I mean, it's the
Throw some shade.
Hey, why is there shade on top of this?
Because there's a cloud up
The
above.
sun is below. Yeah.
Hello, it's a plane.
Yeah, you're right, you're right.
Assume the sun is at.
You're finding, so,
Hello. Okay, so here's the best analogy that I can give you. Remember, when we've done like the Van de Graaff generator, and I would stand there and I would put my hand on it, and it builds up an extremely high voltage, okay? And I put my hand on that, right? And I get shocked, but I don't have to worry about like going into cardiac arrest, which would be bad. It's like, what happened, Perky? I don't know, that's the Van de Graaff generator. So,
such a shame.
okay, that would be awkward. So, what happens is that the electrons, like anything, take a path of least resistance, okay? So, if this says, let's say this has excess electrons in it, for the sake of argument, okay? So, those electrons are looking to balance out.
Let me do it.
So, when I put my hand on there, the only place they can really go is they're gonna try and ground themselves on the earth, okay, and by me being in contact with it. So, the electrons make a choice. Do they go through me, or do they flow over the surface of me to get to the ground? And that's easier if they just flow over the surface. And the same thing happens with the plane, okay? So the plane has this very good conducting surface on the outside of it. So when that gets struck, the electrons basically go, hey, what's our choice? We can either go through the plane or we can get discharged over the surface, and it just gets discharged over the surface. So that's all you have to say.
Okay, that's what I have.
Yeah.
Well,
Yeah.
yeah.
Okay.
That's all you have to say.
He was just wondering.
Yeah, because it's just like water, it's just gonna go the easiest path.
One's possible.
Is that when you lost your papers or when you were,
I guess he took it.
maybe your dad took it where it's like, hey, let's try and work this.
Yeah.
Nerds do that, man.
Yeah.
Okay, anything else?
Yeah.
Going once, going twice.
So, what do you want on top?
I want the textbook stuff on top and the question, the photocopy page on the back. Photocopy page on the back.
What'd you get for sure?
So like, yeah, you end up with an imaginary number.
Multiply
Well, force.
G over divide that by force.
You could do that. That's probably what I was thinking. K Q1 over D squared equals force. Well, yeah, you're right, because that would technically be the inverse. I'm not sure that your distance is right now.
I don't think it's
It was,
looking at 20.
It feels too small.
It won't. No, it's correct. It's correct. Thank you. I got the square.
Yeah.
That's why I drew a triangle, so you have a triangle.
You just have it reversed.
I know, it's very.
Yeah, I guarantee you I do.
Here, try it.
You did silent.
Except because it's imaginary.
That's why you draw the triangle.
Okay. Yeah, that's fine.
That's not yours.
Let's head on back.
yes. Wait, I said.
Oh, no! That's required.
We're gonna have a lab right up before it says.
Oh, absolutely. But you only have to hand it one.
Okay, come on, get the typing, buddy, get the typing.
Because it's like,
Like
they would, if there was
I would rather have a lab right up, but I can.
But yeah,
skip to another 5 minutes.
take that.
My role was the voice
Take
test.
that to the ceiling.
I'm not dictating. Remember last time the time I was in math, I did watch the entire thing and everything. Like all of them. Hey, I did that one. I did that one. I was so mad. I genuinely took 30 minutes to redo all the work. Just even right.
That's the issue.
Those are the like acceleration labs we did. I messed up one of them.
Okay,
I
now,
Like I used deep maybe piece of right.
let's see, this is, because that goes away. So, I don't, Jacob walked me through how he did it, and that's how I got.
Okay.
You could try that. You could try that.
Danny, are we
That's
still
what
going?
everybody else is saying.
Oh, we going?
Yeah.
Okay,
I got a C on that one, though.
so let's talk about this lab. Which I said will probably cause you some frustration, but that's welcome to science. So, the good news is, you're only gonna hand in one per group, okay? Yay! But the bad news is you're gonna get frustrated.
No.
I'm just telling you. So here's a couple of things you need to do. Pick a couple of balloons, I don't care, whatever color that you want. If you want the same color, different color, I don't care. I've kind of got some pastel colors going into Easter, it seems like a good idea. So, you're going to blow them up. I would suggest you blow them up to approximately the same size, okay? Probably about like yay.
How much
Not
would
the
it
most
change everything that we got?
Definitive idea in the world, but you get the point. So, then you're going to take this lightweight thread and you're going to suspend the balloons like such. And I've got paper clips or like those hooks like that up in the ceiling. And then you're going to charge the balloons. I've got Cohen's hair or I've got blankets, okay?
Cohen.
Thank you.
Cohen.
She's not here. Thank you.
Cohen's.
So here's but there is one key assumption that you can make, right? You can assume that the balloons are equally charged, okay? So that's going to make the math a little simpler. So you can just assume that that the two values have the same thing. So you have to figure out what you're going to measure and how you're going to measure it. Now, one of the things you're going to need is the buoyant force, okay? Anybody remember?
But once the
Harsh.
balloons.
Anybody remember how you calculate the buoyant force?
I don't remember the equation, but it's volume.
Rho
Rho VG.
Rho VG,
You find the volume.
okay? Now, what is the density? The density of the balloon
What's a rho?
or the density of the fluid that it displaces?
The density of the fluid it displaces.
And the fluid that it's going to displace is air. And I've given you the density of the air. So clearly, you're going to have to find the volume of the balloon.
Sorry.
So to make this easier, you can assume, even though it's not, but for the sake of argument, you can make the assumption that the balloons are spherical. Okay? So technically they're off by a little bit, but hey, not enough to worry about. So if you can find the volume of the balloon, you can find the buoyant force on the balloon. Now, this is what you have to decide is what you do with the buoyant force, okay? And which direction that's going to act. So, visualize this. You've got the two balloons inflated. You've taken whatever measurements that you're going to need. I'm going to have a scale back there. If you want to find the mass of the balloon, that's cool, okay? Then you're going to charge the balloons, and assuming that the laws of physics still hold, the balloons are going to repel each other, okay? So what you're going to do, and I list this out, okay? There's a bunch of things that you need to determine, right? So the main thing, and you're only going to hand in one per group, but because of this, here's how I want this done. You're basically going to write the procedure in a step-by-step fashion so that Cohen's group should be able to take his lab and give that to Danny's group, and Danny should be able to duplicate Cohen's result. Now, you don't have to get really nitpicky and go, oh, inflate the balloon so that it has a circumference of exactly 35.31 centimeters, okay? You don't need to get that picky, but you do need to say, hey, inflate the balloons to approximately the size of a bowling ball or something like that. So, what you want to keep track of, and this is what's going to be most vital, is the calculations. What do you measure? How do you measure it? Are you going to go define those angles? Are you going to hold up a protractor and try and do that? Are you going to try and measure distances and do it that way? On your diagrams, are you going to go off of the angles in here? Or are you going to go off the angles out there? I don't care, okay? But you want to specify in this write-up so that Danny can take Cohen's calculations or his data and follow that thought process through, okay? So, you want the charge on each balloon and the number of electrons gained or lost on each balloon. So, you can assume that the balloons are going to become negatively charged, which they are, okay? So that'll be a key assumption. So you can assume that each balloon is negatively charged. So you want to determine the gravitational force between the two balloons. So that isn't the gravitational force between the balloon and the earth, okay? You want to use F equals big G M1 M2 over D squared. So imagine that you have these two balloons. What do you need to calculate that value? Mass.
Distance.
There you go. All right?
I remembered one thing.
Yeah. Then you want to determine the fraction of the gravitational force of the electrostatic force. Okay? Obviously, which one's probably going to be bigger?
Electrostatic.
Yes, it isn't like, oh my God, these balloons are getting pushed together because of gravity. So when we get done, I want to set up a big chart on the board back there. And we're going to compare all these data from all the different groups. And we'll see how those numbers compare in terms of electrons lost, charge, gravitational force, what?
That's a lot of pressure for your group.
Oh, it is. It is. That's a lot of pressure.
Public shaming.
Yeah, because if somebody goes, man, everybody else got 10 to the negative 20th and you got 10 to the 5th? Huh. Wow, that sucks.
Uh-oh.
Yeah.
There goes my grade.
Well, so, keep in mind, you're only going to hand in one per group. Okay? You're only going to hand in one per group. So, I'm going to tell you right now, and obviously if you haven't figured it out, you have to avoid you becoming part of the system. Okay? Now, to give you an example, if you remember Henry Cavendish, speaking of gravity, Henry Cavendish was the first one to develop find up with a numeric value of the gravitational constant. If you remember, he had like two large lead spheres, and they were on a torsion wire. And then he had some other spheres nearby, and he knew how much force it took to twist the torsion wire. So he knew the force, and he knew the masses, and he knew how far apart they were. So he was able to solve for big G. So this is dealing with gravity, okay? So he was so worried that his gravitational field created by his mass would impact this experiment. He actually had a separate room added onto his house where he did this experiment so that he wasn't in there, so that his mass didn't affect the results. I don't expect you all to like, oh, we're just going to have a completely separate room added to the school for this lab. But just keep in mind how difficult this is going to be, because if you get too close, you know what's going to happen. You're going to become part of the experiment. So, I'm done. This is going to be due at the end of the block on Monday. All right? So, think wisely, think carefully, be free.